Hi everyone, and welcome to our Simple Circuits 2 exercises lesson. In this lesson, I promised in the previous video to look at a circuit that is drawn in an unorthodox way, but is actually quite easy to solve once we figure out what exactly is going on. And we can take the drawing that they've given us, which is complex here, and simplify it so it actually looks like something we might be given in Year 10 or Year 11 science. So I have a battery supplying a total of 10 volts to this circuit here. And I have 5 resistors, 3 ohms here and 4 ohms here, 2 ohms, 5 ohms, and 5 ohms. We're going to figure out, as in the previous video, first of all the total resistance of the circuit, then the amount of current flowing through the battery, then the voltage across the individual components, and the current through the individual components. The last two, the order of which depends on some quirks in the circuit, which is easier to find first. So the first thing we're going to do is take this drawing here and redraw it in a way that is agreeable to what we are accustomed to. So I'll keep the battery here. And the first thing I'm going to do is, instead of having this diagonal section here, I will split the circuit off and make it clear that this section here is simply a section where the resistors are in parallel. So I have my first resistor here, second resistor there, and one resistor down here. Let me fill in the wires between each of these. This resistor would be the 3 ohm resistor, this would be the 4 ohm resistor, and this would be the 2 ohm resistor here. And then as they come to this point here, well, this point here is that point there. Now I'm going to pretend that I'm grabbing the wire there and elongating it, because for an instant here, all the current from this wire and all the current in this wire flow into one point. So I'm going to take that point and stretch it out as if the metal were malleable. And then we find here we have another parallel section with one resistor 5 ohm and the other 5 ohm, which then comes back down to a point here and then continues to the battery. So that section there is that section there. I am allowed to do all of this, and you can check it. The number one check is I draw a path that a charge might take through this circuit here. If it can't take it through this circuit here, my drawing must be wrong. But if my confidence is legitimate, that will not be the case. I will be able to draw a path through this circuit here, which is achievable through this circuit here. So let's draw the first one. Through those top two, and then through that one and back to the battery. That path here would look like this. So that's okay. Then we do through that 2 ohm and through the lower 5 ohm. Can that be achieved? Yes, it can. And you can try that for every path that you can achieve here. You'll be able to achieve it here. So this is a correct picture of this circuit here. 10 volts. So let's figure out the total resistance of this circuit, because it's the same as this circuit here. R total is equal to, well, first of all, let's collapse this section here. The total resistance of this section, the resistance of this section here, I'll try to avoid using the term total resistance. 1 on R equals 1 on 5 plus 1 on 5. That equals 2 on 5. R equals 5 on 2. 2.5 ohms. So the resistance here is 2.5 ohms. The resistance back here, well, these two resistors we can collapse down to one 7 ohm resistor. So now we have what we can model as a parallel between a 7 ohm and a 2 ohm. 1 over R is equal to 1 on 7 plus 1 on 2. R is equal to 1 on 7 plus 1 on 2 to the power of negative 1. That's what I'll put in my calculator. And that comes to 14/9, or 1.56. So the total resistance of this section here is 1.56 ohms. Notice we said before we haven't said this before, but the resistance of any kind of resistors in parallel, so the resistance of this section will always be less than the lowest pathway resistance. So the lowest pathway resistance here was 2 ohms if a charge were to go this way, and the resistance of this section here is 1.56 ohms. So the total resistance is 1.56 for this section here, plus 2.5 for that section there. 2.5 plus 1.56 is approximately 4.06 ohms. So now we can figure out the current going through the battery. Vt equals IT times RT. V total over R total equals I total, which comes to 10 over 4.06, which is equal to 2.46 amps. Now let's figure out the amount of voltage across each component. I think it'll be easiest to do if we look at this part first. We modelled this not as a parallel section, but as a single 2.5 ohm resistor. And we modelled this section here as a 1.56 ohm resistor. Using these values here, we can figure out the voltage dropped on these sections here. So the first one, 2.5, V equals IR. The voltage dropped is equal to the current, which was 2.46 amps, multiplied the resistance of this section, which is 2.5 ohms. And I have the voltage over this section here, 6.15. So each of these components receives 6.15 volts. The voltage dropped on this section here is equal to IR, 2.46, times its equivalent to 1.56 ohms of resistance. So 2.46 times 1.56 comes to 3.8. I have 3.84. We'll take it to 3.85. So 3.85 volts. So then we add up the voltages, 6.15 plus 3.85, we find it comes to 10. So the voltage dropped over this plus this is equal to the voltage gained by the battery, gained by the charge in the battery. So the voltage across this 2 ohm here is equal to 3.85, because if the voltage across this whole section is 3.85, this receives 3.85. However, the voltage 3.85 has to be split across these two resistors here. So to solve this last part, let's first figure out how much current is going through this section here. V equals IR. 3.85 is equal to I times 2. 3.85 divided by 2 is equal to I. I have 1.93 amps of current going down here. The total current through the circuit was 2.46. So of the 2.46 amps that came to that point there, 1.93 went down this way. That means the difference, 2.46 take away 1.93, which is equal to 0.535 amps, must have gone up there. So there's 0.535 amps running through that top section there. That means the voltage across this component here is equal to IR, 0.535 times 3, which is equal to 1.605 volts. And the amount of volts through that section there is equal to 0.535 times 4, which is equal to around 2.14 volts. If we add up these two values here, we have 2.14 plus 1.605, we get 3.745 volts. That's a little lower than we expected. We expected the same total voltage across here and here, but we can put that down to the approximations we're using. And in the exam, the examiner has a tolerance for you to get a little bit off the answer when you're using decimal places.